Okay, this is term 1, week 9, physics CA, قصدي term 1, week 10. Okay, so basically, this there's شو اسمه there's two great questions you need to know. We'll go over them at the end. But this is a lot. You're gonna need to use the right hand rule like a lot. Okay. Uh, when we get to the questions that need to use the right hand rule, I'll show you how to do it. But for now, let's go through the theoretical part and then we'll go through the actual applied part. Okay, this is from last week. I'm gonna skip it really quickly, but make sure you know this. Okay, but I'm gonna start with 3.9. Storing a magnet. Okay, to store a magnet, you can place them side by side and add what we call keepers. Okay, keepers are used to store magnets. So basically, these keepers will acquire an induced charge and act as a temporary magnet. Okay, that's it. You should know that each magnet will have a soft iron keeper beside it. But you should know what that it's opposite poles. It will never be south, south. No, never. It will be south, north, then north, south. Okay. وكمان you should know if it's south north here, that means this one here will be south, this one should be north. There's a question like that in the quiz, you'll see it. Okay, you should know the 5 ways that would demagnetize a magnet. Okay, storing a magnet without a keeper is obviously one. Heating to a high temperature, dropping a magnet, knocking a magnet, and alternating electric current. All 5 of these you must memorize them. Okay. Okay, now this is where all these practical stuff happens. So over here, basically this guy Orsted, he had an experiment, okay, and he had like a normal circuit, okay, but he put like a compass above and under. Who way he found out that it produces a circular magnetic field. Okay, so basically the compass started rotating. You know that means that there's a magnetic field, and you can find a direction using the right hand rule. Okay, I will explain how to use it once we get to the questions. Basically, the right hand rule, how it works for current, only for current, what happens is you grip the wire, okay, such that your thumb points in the direction of current, and then curl your fingers. Your fingers will curl in the direction of the magnetic field. Okay, I'll explain it when we get to it. Okay. Uh, Now for loops. Okay, we have a rule called the letter rule. And what the letter rule is, it basically knowing the direction of the current, you can find out what direction the magnetic field is. So مثلا if they tell you that the current is clockwise, you draw a circle like this. You know, clockwise goes like this, صح? And then you draw. This is south. Why? Because if you draw an S and you draw an arrow at the ends, it's the same direction, صح? So that means you can memorize clockwise south and then counterclockwise north. But it's good to know the letter rule because sometimes like it's too much to memorize, and I don't advise you to memorize. So draw a circle. Now let's try counterclockwise, anti-clockwise. Anti-clockwise would be like this. صح? Okay. South wouldn't work because look here. Does this work? This looks wrong, right? Let's try north. Put an arrow at the end. Isn't that the same? Yes. Okay. So that means anti-clockwise would be north. Okay. B is what we call the magnetic field. Then we have the solenoid rule. Okay. The fingers point in the direction of the current. Yeah, where was I? Yeah, the fingers point in the direction of the current. The thumb points north into the. Okay, whatever. Let me show you. A solenoid looks like this. Let's say you have a solenoid with current going like this. Heck. Yeah. So it looks something like this. This is the wire, right? Around a solenoid. Okay. Anna, did I explain electromagnets yet? Oh no, it's later. Okay, anyway, so this is the solenoid. Okay, this arrow is the current. Okay, your fingers will point in the direction of the current. Once you coil it, your thumb will point in the direction of the north. So the north, in this case, when you apply the rule, is going to be here, and the south will be here. And you guys know that the magnetic field goes from north to south. It goes like this, goes like this, and this goes like this, and this goes like this. Okay, okay, also from under. This is how it looks. Again, I'm gonna explain the rules all when we get to a question. Okay. A solenoid is a coil which has a diameter that is small in comparison with its length. You may use the solenoid rule to find the direction of a solenoid. Again, solenoid rule, right hand rule, kill one by one. We're gonna explain them just when we get to the quiz. The magnitude of the magnetic field, you should know this. It's directly proportional to the current and the number of loops per unit length. Okay, so if the length doubles, the magnitude of the field doubles. Okay, let's go next. Electromagnets. Okay, electromagnets are very important. A solenoid around a soft iron core constitutes an electromagnet. So this one here, this is an electromagnet. Because you have current, that's electro, and then you have the magnetic field north-south, right? That's how it works. So the iron core serves as an amplifier for the magnetic field produced by the electric current. An electromagnet is a magnet whose field can be switched on and off. This is important. It can be switched on and off. They usually create much stronger fields than permanent magnets. When a current passes through the solenoid, it induces a magnetic field. The solenoid acts like a magnet and magnetizes the iron clip by induction. Okay, la la la. Okay, when a current passes through the solenoid, induces. Yeah. So, you have the solenoid like we talked here. Okay, and this is the current. The current is what on the wires. These are wires that are wrapped around it, electric wires, and this in the middle is iron, صح? Yeah. Why does this become iron? You guys know that we set up that any wire with current inside it has a magnetic field, right? We found out that any wire has a magnetic field. It creates some magnetism. Okay, so basically, this wire that you wrap around this iron, what's it going to create? It's going to create magnet. It's going to create a magnetic field. And since it's wrapped around iron, that iron is going to absorb that magnetic field. And since it absorbs that magnetic field, the iron will thus become a magnet. Okay, so you have now the iron being a magnet and you have electricity coming from the wires. That's what we call it electromagnet. Okay, so what happens when the current passes through the solenoid wire? It creates a magnetic field. The solenoid acts like a magnet. The solenoid is the solenoid. Okay, and magnetizes the iron clip by induction. This is the iron here, or any iron clip that comes beside it. Any object you can bring beside it will become attracted to the solenoid because it's a magnet. These you need to know them. Which of the following are applications of electromagnet? Tape recorders, electric bells, and a relay. You should know that an electric bell is made of an electromagnet that attracts a hammer that hits a gong. Okay, so basically, انت, I'm actually gonna open the book for this. I don't want to draw it, wallah. Like storing magnetic fields, electromagnet. Okay, here. Basically, you have. Okay, this is the electric bell. Okay, what happens is you have this circuit here. You put what do you call it? You turn it on by pressing on the push, and there's gonna be current, right? Current will now pass through the شو اسمه the electromagnet, and that's gonna cause what? Since it's electromagnet, it's gonna cause attraction. Okay, so what's that attraction but why attraction? Because it's a magnet, right? Because there's electricity, it creates a magnetic field, whatever. That magnet's now gonna pull this metal here. It's gonna pull it, and when it pulls it, it's gonna hit this bell here, or what, a gong. They call it a gong, and it's gonna create noise. In your school, I don't know, our school has it. This is how bells work. Okay, حتى when you ring someone's bell, that's what happens. The third one, نحن قلنا أول شيء what؟ قلنا tape recorders. This was أيام, like a long time ago. Now they don't use it anymore. But tape records, you guys, if you know what tapes are, it used to be like different. Okay, the relay. Relay is basically two circuits. Okay, a small circuit over here that causes a second circuit to open. Okay, So this small circuit here, when you turn it on, current is gonna flow through the electromagnet, and again the electromagnet will create a pull. It's gonna pull this strip of metal. It's gonna pull the strip of metal. When this pulls, it's gonna cause this here to go up. It's like a hinge. So if you pull this one down, it's gonna go up here, and it's gonna cause these two to stick together, like over here. I don't know why I'm drawing it, but it's like right here. So it pulls this here, and it goes up. It causes the contacts to close the circuit. So the second circuit that's up will now be closed, and it will actually start having a current inside it. So you should know that the relay is formed of two circuits. What are the advantages of it? That one small circuit can be used to control another circuit. The input circuit, the small circuit, can work on a low voltage supply. So you just need a small voltage supply which control another circuit that can work on a high voltage supply. This is important, for example, in cars. When you start a car, I think they talked about it in the book. They didn't talk about. Yeah, here I think this is a car. So you have an ignition. You put in the key. You close it. The key. It closes a small circuit, right? It closes a small circuit, and that small circuit starts the whole car. Okay, that's how you can think of it. A small current in the input circuit is used to turn a large current in output circuit. For example, oh yeah, they talked about it here. A car ignition circuit. That's up here. So this is the motor, whatever. It can be considered as a mechanical current amplifier. It can be used as a level sensor. These are things you need to memorize. Okay. هلا relay. I think I talked about them. Which attracts and hinges the second circuit to close, has 5 advantages. Okay. The reed switch. Okay, it works like a relay. The effect. Okay, the reed switch. I just wrote reed switch. What is the reed switch? Oh, so basically they're saying the reed switch. You know how there's two circuits. The relay is here. The reed switch is the thing that's the second circuit. Okay, that's it. They don't ask these بس يعني يلا. Okay. The effect of an external field on a current. Okay, this is you should know. A current subjected to a magnetic field direct perpendicular to it is acted by a force perpendicular to the plane of field and the current. So if you have current that has a perpendicular magnetic field, it will also have a force. Okay, that's you need to know that. IBF. Memorize IBF. You're gonna need later for the quiz. IBF. Okay. The magnitude and direction of the electromagnetic force depends on the direction of the magnetic field and the current. Obviously, the force depends on, we said, the current and the magnetic field. The electromagnetic force, what does it depend on? It depends on the magnitude of the field and the magnitude of the current. Again, IB will get you F. I is current, B is magnetic field, F is force. Again, use the IBF right hand rule method, which we will explain in the quiz. Okay, the electromagnetic force can be found using, you need to know these three: the right hand rule, the motor force rule, and the corkscrew driver rule. Okay, you should know these three. If current and magnetic field are parallel, you should know this also. This is very important. If current and magnetic field are parallel, no force. We said they must be what? Perpendicularly, right? A constant current is never affected by the field it creates. Only affected by magnetic field. Depends on the. Yeah. Okay, basically what this is saying is, let's say this is a wire, and you have, this is the magnetic field around it. If it's going up, it's gonna be something like this. Okay, what they're trying to say is the current isn't affected by the magnetic field that it produces, right? Like the magnetic field it produces doesn't affect this current. But let's say you have another wire and it has its own magnetic field like this. Now, this magnetic field would affect the current here. That's basically what it's trying to say. I'm just trying to explain to you. So you should know that the current is never affected by the field it creates. Okay? Okay. The magnetic field through A is defined as the product of the field. Okay, as the magnetic flux. Magnetic flux is defined as the product of the field by its area. This is the formula. Memorize this. Magnetic flux is equal to BA cosine theta. Okay? There are now cases you must memorize. The first case is that theta equals 0. Okay? Cosine 0 is 1, and that is when you have maximum flux. How does it look? This is how it looks. Let's say you have, this is your current, okay? And this is your magnetic field, okay? They're perpendicular to the current. Let's say this is the current here. Okay. This is the first case. When is theta 0? This is your plane here. You'll be like, oh, Walid, it's perpendicular, isn't theta 90? No. When we say theta, it's the angle it makes with it of the normal. The normal here, this is the normal here. If you take the normal down here, it's actually along the magnetic field. So theta is 0. So when is theta 0? When it's actually, when the thing is perpendicular to the magnetic field. Okay? The second case is when you actually have an angle. I drew it here. This is the normal here. This is the normal. This is the angle. So you take the angle between the normal and the magnetic field. And then the last one is theta equals 90. Let me show you. This is the magnetic field. Okay? This is I, this is B, whatever. And this is your plane. That's the, no, sorry. Not like this. Okay? And this is over here. People say, no, this is theta equals 0 degrees. But no, remember we take the normal. This is my normal. This is the magnetic field. What's the angle between it? This is 90 degrees. But when it's 90, you know, cosine 90 is 0. That means the flux is 0. Okay? Remember, BA cosine theta. Okay. Okay, the rule of maximum flux. You should know this. When a current carrying coil is placed in a magnetic field, okay, magnetic forces will act on the coil in a way to increase the flux entering the south face. You must memorize it. Basically, how does this happen? انت if you have قول flux هيك. Actually, no, let's go back here. Let's say you have, this is your plane here. It's actually like, this is a 3D shape. It goes like in هيك. Okay, imagine this is how it looks. Okay, but نحن we just draw one line. Let's say this is the south face, this is the north face. Basically, there's a few exercises that happen, but there's going to be forces that drag it down like this and drags it up this, creating a moment that will eventually sorry, no, the other way around. The other way around. This is south, this is north, and this is gonna drag it up there like this. So it's basically gonna become like this. So the forces will turn. Like it will turn to maximize the amount of magnetic field entering the south face. You must memorize this, okay? When a current carrying coil is placed, magnetic forces will act on the coil in a way to increase the flux entering the south face. Okay? هيك نكون خلصنا النوتس. هلا let's go to the quiz. I'm gonna skip anything that needs a rule with the right hand and we'll come back to it at the end. I'll show you at the end. Okay? The magnitude of the magnetic field created by a current carrying wire is directly proportional to the current, and we said the number of loops. But here they're saying inversely proportional to the distance from the wire. Okay, so they're saying from the wire, so it's distance from the wire, inversely proportional to distance of the wire. Memorize this, okay? If they said directly proportional again, you would say number of loops. Okay. Question 2. Which of the following would demagnetize a magnet? Obviously using an alternating current. Did we say room temperature? No, we said heating, right? Dropping a magnet, yes. Keeping a magnet in a dry place, no. Storing a magnet without a soft iron keeper. These all would demagnetize, as well as over here, as well as heating to high temperature and knocking a magnet. Question 3. Which of the following are properties of electromagnets? Electromagnets are made by winding a current carrying wire around an insulating core? No. Electromagnets are permanent magnets? No. Electromagnets stop being magnetized when current through them is off? Of course. We said that electromagnets can be switched on and off, right? The role of electromagnet's core is to increase its magnetic field. Basically, without the electromagnet core, you won't have any electromagnetic field. Remember, we said that the core of the solenoid here, it absorbs the magnetic field of this electric current and amplifies it and creates an electromagnetic force. Okay, the direction of electromagnetic field can be changed at will. Yes, because you can change the direction of the current, which would change the magnetic field. Question 4. Which of the following are common applications? Okay, we said tape recorded, relay, and fire alarm bell. Also, في reads. صح? Question 5. The magnetic flux to region A is defined as a product of what? Remember, flux is equal to BA cosine theta, right? So it's a product of the magnetic field B and the projection of the area perpendicular to B. Okay? Why do we say perpendicular? Because remember, we would take the normal. The normal is always the one perpendicular. You take the angle perpendicular. Okay. A magnetic field B makes an angle of theta with a square-shaped elastic frame L placed into it. Which is funny, would double the magnetic flux through the frame. Remember that the magnetic flux, remember at the end, the magnetic flux, oh no, not here. I said it somewhere. Yeah, I said it somewhere. Yeah, here. The magnitude of a magnetic field we said is directly proportional to the current and number of loops per unit length. So if you want to double the magnetic field, then you double the current or double the loops. So which are they said magnetic flux? Oh wait, no, that's something completely different. Yeah. Remember, magnetic flux is B A cosine theta. So what's it? It's directly proportional to the magnetic field, the area, and the angle. So cosine of the angle, not sine. So if you double B, obviously you're gonna double the flux. Double A, double the flux. Double cosine theta, then also you're gonna double the flux. Okay. Question 7. Okay, this one here, you need the right hand rule for it. We're gonna come to it at the end, so I'm gonna write down question 7 on the side. Okay. Question 8. This one also requires the right hand rule. Okay, we'll come back to it again, or solenoid rule. Okay, the magnetic field inside the loudspeaker is what? It's axially symmetric or axial radial field. Remember what we call it over here? Let's go back to page 1. Oh, over here. The inside the current meter, it was plane symmetric radial field. In the loudspeaker, it's we called axially symmetric. Okay. So loudspeaker is actually symmetric radial field. The current meter is plane symmetric radial field. Which material is not used in the experiment that demonstrates the dependency of the electromagnetic force on the direction of the current and the magnetic field? Obviously, the reed switch mankhas, but I want to see what are the other options. Uh, what are the other options? Question 10. Okay. Power supply, U-shaped magnet. Oh, okay. The electromagnetic force depends on the direction of the current and the magnetic field. Remember, I, B, F, right? Increase I, F increases. Increase B, F increases. For current, how do we know? How do we? Remember, it was a circuit Orsted's experiment over here. Orsted's experiment. If I show it in the book, it was here. Okay, Orsted's experiment. Basically, you have a magnet, you have a rheostat. You have a power supply. يعني you have a power supply, you have a rheostat. Obviously, you have copper wires, conducting wires. A push button switch. You need a switch, right? A switch. A U-shaped magnet. Of course, you need a magnet. Power supply, reed switch. We never said reed switch. Reed switch is something completely different. Remember, reed switch we said was an application of an electromagnet. ما كانت. It was not. It was not something you need to show the electromagnetic force. Okay. Question 11. Okay. The two factors that electromagnetic force depends on are current and magnetic field. Remember, I, B, F. Right? It's here. F depends on B and I. Question 12. Show the correct shape of the magnetic field of a solenoid. This one, I'll come back to it as well. This is question 12. Question 13. Okay, radial fields are fields that awaken away from the center and which remain uniform at a constant radius from the center. Which one is an actually symmetric radial field? Yani loudspeaker. Memorize this. Loudspeaker consists of a round one outside and another round one inside. North is outside, south is always inside. This one memorize it. If they said for a plane symmetric, this one would be plane symmetric. Okay, if they asked it. Such magnets that are actually symmetric are used in loudspeakers. Yeah. Question 14. This one is about storing magnets. Drag and drop to show the induced poles of the diagram. أكيد. نحن يا الله, where did I go, man? وين أنا store magnets safe. Of course, أنت you have north, so هيكون في south. I told you always that if it's north here, south is here. And here you have south, so أكيد there will be north here. Never like poles. You can never have like poles. The gray bars, what do we call them? They're called keepers, and they are made out of soft iron. Remember, نحن we call them soft iron keepers. Question 15. This one كمان, we need the right hand rule for it. We'll come back to it. What are the rules? Henny, the right hand grip rule and the Maxwell screw rule. These are for the current. For current, there's two rules. You can use the right hand grip rule and the Maxwell screw rule, and I don't like using the Maxwell screw rule. Question 16. Okay, when a student looks at an end of a solenoid, she notices the current flows clockwise. What is the okay? Come on, we'll come back to this one. Question 17. In order for the magnetic force to compensate, again, this one we're gonna come back to it also. And yeah, for the magnetic field, there's three rules: the right hand rule, the motor force rule, and the screwdriver rule. Okay, these three rules are for magnetic field. But for current, in a straight current in a wire, that one is Maxwell screw and right hand rule. Okay, rank the diagrams in accordance with the magnitude of the magnetic flux. The one with the smallest flux is 1. Obviously, the one with smallest flux is the one with straight, right? Remember, we said this because theta in this case is 90 degrees. Because if we draw the normal, it's 90 degrees. Okay. Obviously, the strongest one would be this one which is standing straight, because here theta is equal to 0 degrees. Because cosine 90, by the way, is 0. Cosine 0 is 1. So obviously, the best one would be when theta equals 0. So this is the weakest. This is the strongest. The one that's closer to being straight is the closest one to being strongest. So which one's closer to being straight? This or this? Okay, this one. So this is 3. And this one it's closer to being flat. With the flat ones, I have 0 flux. Okay, so that one, it's the second weakest. Question 19. Okay, how will the iron... Oh, I deleted all the... Ya Allah. How will the iron filings orient themselves once the current flows through the electromagnet? So basically, they put an electromagnet and they put iron. What's going to happen to the iron? Obviously, since there's an electromagnet, they're going to be attracted. But how will they arrange themselves? Parallel to the axis of the electromagnet. Because the electromagnet would be like... how can I say it? It would be like this. This is the electromagnet, and it's like here. Okay. The iron would also be like this. Okay. They would be parallel to the axis of the magnet. Okay. Which of the following best describes the magnetic field inside electromagnet connected to a DC circuit? Obviously, the field is uniform. It's a uniform field. Halla, I think we said question 7. Question 7. Okay, yeah. Okay, for the magnetic field, first I'm going to start for the magnetic field in a current carrying wire. Basically, you have a wire, let's say, I'm going to first, before that, I'm going to show you two representations. You can either have an X or a dot. An X is into the page, and the dot is out of the page. Whether it's current, whether it's magnetic field, whatever. You need to know. So let's say you have, they show you this. And they ask you to draw the magnetic field around this wire. This is a wire coming out. So this is what you do. I'm going to turn my camera on just so you can see. Okay, so basically, how you do it is you have your right hand. It has to be your right hand or it won't work. Your right hand, okay? For the current carrying wire, your thumb will be the current. Your thumb can either go in, okay, inwards, or it can come outwards towards you. For this case, it's out of the page, right? So it's going to be out. Now, you want to know, where is the magnetic field? The magnetic field can either be clockwise, clockwise, like this, clockwise, or counterclockwise, right? And I want to know, is it clockwise or counterclockwise? Here's what you do. You take your thumb. We said it's out of the page, so it's going like this. Now you take your fingers and you curl them. Curl your fingers. It's going to go like this. It's going to go like this. So it's going to go like this, right? What is that? That's counterclockwise. So then let's say they ask you to label it, it's going to be counterclockwise. Let's see this question 7 over here. Enter, you have an X. So that means it's going into the page. So it's going to be like this, okay? You take your fingers now and you're going to curl them. If it's into the page, take my fingers, curl them. They're going to go like this. So that means that's clockwise. So it's going to go like this. So let's label it. It's obviously going to go like this, like this, like this, like this. That's for the current in a wire, okay? Hella, I think we said question 7. Yeah. Now, I think the solenoid rule is almost the same thing. Now we have for a solenoid. The solenoid also has its own rule. It's called the solenoid rule. Let's say you have a solenoid like this, and you have, it goes like this, and it goes like this. 1. Okay. So this is how it is. They ask you, determine the direction of the magnetic field. Until you have the current, you need to now know the direction of the magnetic field. Where is north, where is south? To know the magnetic field, you need to know where is north, where is south. For the solenoid rule, again, you take your right hand. This time, instead of using my thumb, I'm going to use my fingers. Okay? My fingers, they're going to be coming from behind. Okay? They're going to be coming from behind. You curl, so you curl your fingers in the direction of the current in the solenoid. The current, in this case, is coming from behind and coming towards me. So I take my fingers, I curl them towards me. When I curl them towards me, take your thumb and extend it. Where is it extending? It's extending to the right. So in this case, where's my north pole? It's to the right. So the rule for the solenoid is take your fingers and curl them in the direction of the current. Your thumb, after that, will be pointing in the direction of the north. So in this case, since I'm curling towards me and my thumb is going to the right, that means the north is over here and the south is over here. And now can I know where the magnetic field is? Yes, I can. It's going to be from north to south, right? Like this. And you also have a line going like this. That's for the solenoid rule. So over here, they drew it like this. They told me it's coming down, right? So same thing. I take my hand and you curl it towards, like downwards, right? Like this. Where's my north? It's going to be on the right. So that means you take your north right. That means this one here is also south. So it goes like this. This is your magnetic field. So it's going from point A. Where's it going? Into the south. So it's going rightwards. Okay, that's how it works. Hold up. Question. For this one here, they're saying select the picture that shows the correct shape of the solenoid. Same thing, solenoid. But here, they didn't draw the solenoid, they didn't draw the current. But what did they give you? They gave you this and they gave you this. Remember, this means out, this means in. So it's going out of here and into here. So they basically drew it for you. So same thing, until you have now the direction of the current of the solenoid. Can we find the magnetic field? Of course we can. We need to know our north and south. This is the same exact solenoid that we used in the past 2 questions, so I'm going to speed up a bit. You curl it down. Where's my thumb pointing? To the right. So the north is over here, the south is over here. So now since you have the north and south, just draw the magnetic field. It's going to go like this. And you always have a line going in. So it looks exactly like that. Going out of the north into the south. Okay? Let me see now. This is same as question 7, but they just added a part B. So part A, again, let's do it again. Now they're telling us about a current carrying wire. So we're going to use the first rule, right? So again, the X means in. So in, and then curl your fingers. It's going to go like this. So that's going to be clockwise, right? So clockwise. So it's going to be like this, right? Okay, which rules can you use to determine the direction of the magnetic field produced by a current? Remember, for the current, it's only 2 rules. It's the right hand and the Maxwell's rule. I didn't mention the Oh, no, I did. I mentioned the Maxwell's rule, but I didn't show you how. I'm not going to show you how because I don't know how, aslan. Just use the right hand rule, okay? Question 16. Okay, this one, yeah. This one's a bit confusing. Here, when a student looks at an end of a solenoid, she notices that the current in its loop flows clockwise. What end is she looking at? Here, there's no rules with your hands. We're gonna use what? We're gonna use the letter rule. What does the letter rule say? Let's see. We have our. You draw your circle. You draw your magnetic field. They said it's clockwise, so it goes like this. Which letter, south or north? Let's see. Let's try south. South. If you draw an arrow at its ends, does it correspond to the direction of the current? Yes. So that means that is the south pole. To prove that it's not north, again, let's draw clockwise. If I draw north and I draw arrows at its ends, this is opposite. This is going up, but this is going down, and this is going down, but this is going up. So of course, it's not going to be north. Okay? The magnetic field in such solenoid is directed away from the student. If she's looking at south, you will think, oh, south pole is going towards the south, no? But look here. Let's say you have the solenoid. I'm not going to draw the currents because it's going to take time. But north-south, it goes like this. Looking at the south, how does it look? It's going away from the south. صح? You get what I mean? So the student is looking at south. So looking at south is going to go away. Okay? This one here uses the IBF rule. Okay? The IBF rule is very, very important, and many students they get confused. They get confused when they use it. How the IBF rule works? You'd be asked to find the force. Usually they gave you. To find the force, there's 3 rules. Okay. There's the right hand rule, the motor force rule, and the right hand screwdriver rule. I don't really use the right hand screwdriver rule. I'm gonna start first with the right hand rule, and then I'm gonna do the motor force rule, and into whichever one you find easier, you choose. The IBF rule, how it works. Actually, I'll just start here. The IBF rule, you have 3 fingers. Okay, you have your thumb, your index, and your middle finger. Okay. The thumb is current, your index is the B, which is the magnetic field, and your middle finger is the force, F. Okay, so I, B, F. Always you use your I and B, and they usually ask you to find the force using your middle finger. Okay, let's say, مثلا, the current was going out, and they gave you that the magnetic field is going to the left, and they'd ask you to find the force. So you go out, left, and now you want to know where the force is. You know, current is the thumb. Your second finger is the magnetic field. So current, magnetic field, I need the force. I always use the middle finger for the force. You don't even need to do anything. Just stick your middle finger out. Stick it out. Where's it pointing now? Down. So that means the force is going down. Okay? Now, the motor rule. The motor rule, some people find it easier, some people find it harder. Okay? The motor rule is you take your fingers, instead of using I, B, F, you take your fingers as both I and B, and your thumb is the force. So let's say your current is going inwards. Okay, let's say current is going inwards, so you're going to point your fingers inwards. Okay? And the magnetic field, if it's either left or right, you see now. Let's say they said magnetic field is to the right. So I point my fingers inwards to the right, and I point my thumb out. Where's my thumb pointing? Upwards. So that means the force is upwards. That's a motor force. You point your fingers in the current and magnetic field. So let's say now left, or no, let's say they were going out. Let's say they were going out to the left. Where would the magnetic field be? Up. Okay, let's say out to the right. It would be, hold on. Yeah. Sorry. Out to the left. You'd point it like this. Out to the left. Stick your thumb to be down. This is why I don't use this rule. I don't like it. I prefer using IBF. So for this question here, a current carrying wire is parallel to the ground. The current flows inside the plane of the picture. So it's going in, right? So current is going in, or like this. Okay. Here they don't ask for the force now. What they're saying is they want the magnetic force to compensate the weight. So basically, they're saying the force is compensating the weight. What direction is the weight? The weight is going down. The weight is about to go. The weight goes down. If we want to compensate the weight, that means they want the force to go up. So they gave us 2 directions. They gave us the current is inwards, so it's like this, and they gave us the force is up. So I have this like this now, right? I want to know where's the magnetic field. What finger's the magnetic field is the index, right? So just stick it out. Where's the magnetic field going? To the left. So that means the magnetic field should be leftwards. What are the tools you can use in right hand motor force, right hand screwdriver? Okay, let's see, is there anything else? Okay, there's nothing else. Thank you so much for watching, and good luck in your CA.